Okay, so last week we finished chapter 2 when we looked at arithmetic, and we've already looked at ancient Egyptian and Babylonian math. Okay, and so one of the things that you should have seen is that the ancients had a different view of number than we do. So if we look, for example, we look at the Babylonians, we see that they're very good at computation. They can do all kinds of amazing kind of things. But they like to think in terms of whole numbers. And so, for example, when if they have the fraction a half, they'll write that as 30. And they kind of see there's kind of no difference between 30 and a half. For them, it's just kind of like a matter of units. You know, like it could be 30 minutes, it could be 30 hours. You know, everything is kind of like a whole number, really. Even when you go to fractions, all you've got to do is you don't change the number, you just change the units. And that's how you kind of zoom in, getting smaller and smaller. But there's this kind of idea, if you think about it, there must be this idea in the back of their mind that all number is really just counting. Okay? And so if we think of just like number in its simplest form, it's the positive integers, like it's 1, 2, 3, 4, it's the counting numbers. And that's obviously a starting point, but we kind of know that there's more to numbers than that. So, for example, there's 0 as a number. And that's, the fact that 0 is a number is a kind of a modern idea. Even back when the Indians invented 0 as kind of like, they only use 0 as kind of like a placeholder. They mean really that it's empty. It's almost like it's non-defined. So, for example, there's, I think, a medieval Islamic text where they talk about, you know, what angle has a sine greater than 1. Okay? We all know that that doesn't exist, right? Because sine has to be between minus 1 and 1. But they say, oh, if the sine of that is greater than 1, the answer must be 0. Okay? And so obviously when they do that, they're not talking about 0 as a number, they're talking about a 0 as like how we would say does not exist. Okay? And you know, they don't really think about negative numbers. And at this stage, we can even see they're kind of having a little problem with, you know, fractional parts of things. And so, for example, like I said, the Babylonians like to think in whole numbers even when they're doing fractions. The Egyptians, you know, we saw how they were kind of put off by a concept like 2/7. They would have to go through and they would have to figure out how to write 2/7 as a sum of unit fractions. Okay, so we kind of see, you know, they can do arithmetic, they can do all these sort of computations, but sort of their logical basis for how they consider number is not, they're not worrying about it. Okay, so now what we're going to do, we're going to be starting talking about geometry, and you guys are going to start talking about the ancient Greeks. And here now we see kind of like the concept of number sort of being examined on a more kind of logical setting. Okay, so, and the reason that's possible is through geometry. So we did arithmetic before, and you would think that the natural thing that you would do after arithmetic is algebra. So in our minds, arithmetic then algebra is just like kind of like the natural progression, but we can't do that. We have to do geometry first, because what we're going to see is that algebra is going to come up from geometry. And so that's what we're going to talk about. Okay. So, is that okay? Okay. So, we're going to look, I'm going to be talking about Islamic geometry, and you guys are going to be talking about Greek geometry. It's going to kind of be the same thing. Because for the medieval Islamic mathematicians, there were kind of three pillars of their geometry, and they are three famous Greek mathematicians who we're going to be talking a lot about. And so remember, I told you that around 800 in Baghdad, they set up the House of Wisdom. You know, we would call it a university, but its main function was a translation bureau. So it was taking works from Greek, Sanskrit, Persian, taking it, and they were translating it into Arabic. And they were not only translating, they were writing commentaries. So that's like the standard way they did things back there. So you would do a translation, and then you would make some comments on it. And it's those commentaries that were kind of how the mathematics progressed. And so they wrote commentaries on Euclid. These three mathematicians are kind of different in how they regarded and how their works were regarded. So Euclid wrote the Elements. And the Elements is really the most successful textbook of all time. It went from 200 BC to basically the 19th century. It was the way that mathematics was taught. And it still even influences how you were taught in high school, because you probably all did some kind of geometry class where you did stuff with triangles and circles, and that all comes from Euclid. And a lot of the Elements is not Euclid's work himself. They think that one of the books was his kind of work, what he worked on, but most of it was just what the standard Greek mathematics was of the day. And the mathematics was geometry. This is supposedly when Plato had his, did he have the Academy, was it the Academy or the Lyceum? Well, whatever Plato's school was in Athens, supposedly over the door was written, "Let no ungeometrical person enter." So for Plato, geometry was, the mathematics. Next person is Archimedes, who is considered the genius, the greatest mathematical genius there was before Newton. And so his works are at absolute tour de forces. They're just kind of amazing, and the Islamic mathematicians read them and they were really inspired by these works, and in their commentaries they then tried to do further stuff. So, for example, there's a famous one on the sphere and the cylinder, where he's talking about the volume and the surface area of a sphere and a cylinder. And in its introduction, he mentions another paper that he did where he talked about what the area of a parabola was. And the Islamic mathematicians didn't have this, right? Because it has been found now. They found it later from Greek sources, but the Islamic mathematicians then reconstructed it. They actually they were inspired to that is a problem that we're going to work on, and they went and did it. So the heptagon in the circle, we'll look at that one. That's a pretty amazing paper. It actually it's not known from Greek sources. It's only known from Arabic sources. And it's a pretty wonderful little work. And then the third is Apollonius of Perga. who sort of sits in between Euclid and Archimedes. He wrote this book, the Conics, which consists of 8 books. So when the Greeks talk about a book, they really kind of mean like a part, you know, be like part 1, part 2, part 3, how we would do. So the Conics has 8 books. Only the first 4 books survive from ancient Greek. And for a start, you've got to think, what does that mean? If the book doesn't survive, that's because it wasn't used. And this is because the Conics is kind of like the Elements. It gives this, it's famous as being, you know, the most comprehensive treatment of one particular subject. And most of it actually was Apollonius's work. But it's kind of difficult because it's kind of like, it develops kind of like a research kind of problem, and it develops it quite a bit. In Arabic translation, the first 7 books survive. So that kind of shows you how good the Islamic scholars were, because they could keep up a little bit more with Apollonius than could the later Greeks. And there were actually attempts done at reconstructing the eighth and final book. So so it's this geometry that we kind of want to look at. Now, why was geometry so important? Well, geometry is important really for any kind of civilization, because, you know, you want to build things, you need architects and that, you need craftsmen to do things, and kind of geometry just turns out to be actually to have useful practical skills that way. Another thing is that geometry is useful in constructing various instruments, scientific instruments, things like sundials, astrolabes. So just to be able to construct these things and work things out, you need kind of geometry. Another really important thing is when you look at astronomy. So as I said before, astronomy has been an important field right from the ancient times. It's been a big motivation for doing mathematics. But ancient astronomy is not like modern astronomy. So modern astronomy we can think of as being astrophysics, and that was invented by Newton, you know, in the 1600s, when he, you know, came up with the law of gravity and then was able to do what we think of mechanics in space, astrophysics. Before Newton, astronomy was kind of like, they did kind of number theory, because they were dealing with, you know, planets moving with orbits of every 7 years and something moving every 12 years. So when are they going to line up? So you've got to solve 7x plus 12y equal, you know, some sort of linear relation. But also geometry was at the core of it. Sort of like setting up these systems of circles and triangles, because like how, we'll get into this when we talk about how ancient astronomy was done. But the key part of ancient astronomy was geometry. And that kind of led to trigonometry as well, just like modern astronomy is kind of based upon, you know, the law of gravity and that kind of mechanical physics. And finally, the reason why they loved geometry was just in the logical treatment that the Greeks gave to geometry. And this really has survived into modern mathematics as well. So the whole idea of proof to do things, that's kind of like a Greek invention, because it's how they did things. They were really into philosophy and arguing and doing all kinds of things. And later we'll see why why they needed to do that. But the thing is, once people saw the treatment that the Greeks gave to the logical treatment that they did things, particularly from Euclid, mathematicians in other cultures loved that. So, for example, I've talked about the Chinese. The Chinese were very strong at mathematics. In the 1500s, when the Portuguese Jesuits went to China and they first showed the Chinese mathematicians Euclid, the Chinese mathematicians went gaga, but they said, oh, wow, this is the way that we should do mathematics. It was just so intellectually stimulating and seductive that they went that way. They went to the, I don't want to say dark side, whatever the other opposite of the dark side is. Okay. So, when people start doing Euclid, one of the things we're going to be talking about is geometrical constructions. And that's what Euclid jumps into straight away. So remember how Euclid works is he sets up like a bunch of postulates and axioms. And from that, he then sort of argues. And so this is a thing that was seductive to other cultures. It was also super seductive to philosophers. So if you look at people like Thomas Hobbes, Spinoza, Immanuel Kant, René Descartes, Bertrand Russell, philosophers all through the ages, when they've seen Euclid, they've gone, wow, this is how I want to do philosophy, right? I'm going to start off with obvious truths, and then I'm going to conclude, what is the ethical way to live? So this way of thinking, as I said, is super intellectually seductive. And so Euclid, when he starts off in his axioms and postulates, he basically says that here are your tools that you can construct things with: a straight edge and a compass. And it's a straight edge. It's not a ruler, so it's not got any markings on it. And it's a collapsible compass, so you use it, and then afterwards it goes back to the thing. So what it's basically saying is you need 2 points, and if you've got 2 points, you can construct something with it. You can take your straight edge and you can draw a line between those 2 points, or you can take your compass and you can put one at one point, one end at one point, and one end at the other one, and then you can use one as the center of a circle, and the distance between the two is the radius, and you can draw a circle. Okay? So there's no, at first glance, there's no way that you can sort of transfer lengths, which is kind of obvious thing that you want to be able to do, right? So the first thing that Euclid does in book 1 is his first 3 propositions shows you that you can transfer length, and that your straight edge can be regarded as a ruler, and your compass can be regarded as something which is non-collapsible. Okay? And so let me show you those first 3 propositions. It's very sort of straightforward. So the first one is, given a segment AB, to construct an equilateral triangle ABG. Okay, and so it's pretty easy. You just take your compass, you put one end at A and the other end at B, and you just draw a circle like this. And then you swap. You make the center B, and you put the other end on A, and you do an arc like that. And then when they intersect, you let that be G. And then you've got points A and G, so you can do a straight line there, and you can do a straight line there. And it's very easy to convince yourself that you've got an equilateral triangle, right? Because the radius is kind of like the same. Okay, that's proposition 1. Proposition 2 is given a segment AB, and some point, let's call this point D, that we can take this segment AB and we can make a segment of the same length, which one of its endpoints is D. Okay, and that's actually pretty straightforward. So what you do is you make an equilateral triangle whose side is AD, and we can do that because, yeah, proposition 1. Okay, and let's call this G. Okay, and now we can extend this straight line AG, and we can extend this line DG, and then we can get our compass, and we can put the compass with the center at A and the other end at B, and then we can just make a little circle here, and it's going to intersect here, and obviously then what's a letter we haven't? E. Obviously, AE is the same as AB because they're both radii of the circle. And then you get your compass and you put one end, the center at G and the other end at E, and you make a big arc like that. And it's going to intersect here, say at W. And DW is going to be the same length as AE, right? Because this is the same length, this is the same length, so this has to be the same length because there's a proposition in, no, it's a postulate or an axiom that equals minus equal something like that. You've got two things the same, and you remove from same things, the result is going to be the same. So that's there. And then finally, proposition 3 says you can transfer lengths. And what does that mean? That means we need our AB here. We need our point D over here. The only thing that's missing from proposition 2 is the orientation of the line. And so we can say, well, we can have the line here in a given orientation. So it's on some line DE, right? So not only have we got the length, but we can get the orientation right. And again, what we just do is we just use the first two. By the second proposition, we can call that Z. We can transfer to point D a segment of the same length, but not necessarily the right orientation. But once we've got it there, we can then put it onto the right orientation we want just by taking a compass, putting it at D, putting the end at Z, and then making a circle. Making a circle, I said, and because they're both radiuses, they're going to be they're both radiuses of the same circle. They have to be equal length. Okay, so this is the famous start to Euclid's elements, and this is what blew people's minds. You start off with the assumption that you can't transfer lengths, and you end up concluding you can transfer lengths. And new share. Where was I here? So this is what's so intellectually seductive and stimulating. We know it by the name as Occam's razor. So that if you can say the same thing with less input, if you can sort of pare away what your assumptions are and come up with the same result, that's considered better. It's prettier. People think it's more beautiful intellectually. And this is a thing that, as I said, the Chinese mathematicians, when they saw it, when people like Immanuel Kant thought when they saw it, they thought that was kind of amazing. And when the medieval Islamic mathematicians saw it, they also thought the same thing. Okay, so, and then there's all sorts of other constructions you can do that that's there in book 1 or so of Euclid. Given any segment and given a point, you can make a perpendicular line to it. Again, you just use your compass to go ahead and do that. You can divide a segment into an arbitrary number of equal segments. So let's see if I can do this on the board. So say we've got a segment that we want to split into thirds. So what do? Well, we know how to construct perpendiculars. So we construct perpendiculars one way, and we construct perpendiculars another way. Then we just come up with some arbitrary length. And we mark off equal lengths like this. Right? And then I think what happens is we just then join these lines like this. Oops, that cuts it into 4. Okay, I split it into 4 equal parts. Yes, of course. Mixed up intervals and endpoints. Okay. But here, this is some arbitrary length that you just made up, but then these are actually cutting your segment into equal parts. And so here we start getting at what number is meaning to the Greeks. Hang on, I'll get that in a minute. Another thing you can do is bisect an angle. So, like if you've got an angle like here, you can just mark off an arbitrary length here. Then you go to this endpoint here, and you mark off another circle here, and where they intersect, that gives you a point that you can go there, and that's going to bisect the angle. Okay, and so what Euclid does, he gives these constructions, and then he proves that it does what he says it's going to do. You can also, by these constructions, if you're given a circle, you can then come up with a diameter of this. You can find a diameter of the circle. If you're given a circle and a point, he tells you how to then construct a circle with that point as its center and it being tangent to the other circle. So all kinds of interesting kind of things like that. And then he proves that the construction that he gives is actually valid. Okay, so It turns out then that you can do arithmetic with geometry. So I'm going to call this constructible arithmetic. So by these constructions, you can do arithmetic. Now, what are you doing arithmetic with? If you want to do it with angles, you're out of luck. Because the best you can do with angles is you can bisect them, as I've shown you before. Someone's going to be talking about the problem of trisecting angles, which turns out to be one of the famous problems of Greek geometry that annoy them because they couldn't do it. But you can do arithmetic with lengths. You can add, subtract, multiply, and divide lengths. And so you get this arithmetic of proportions. Okay, so we're getting some idea of what number is now. So to the Greeks, we can think of number as being a length. Okay, so I've already told you that 0 was not thought of a number. To the Greeks, 1 was not thought of as a number, right? Because 1 is the monad. 1 is the generator of numbers. And we still kind of see it in our everyday speech, right? Because when we say a number of us are going to the movies, we wouldn't think of 1 as being that kind of number. So 1 is kind of special. And so how would we go about doing this? How would we go about doing arithmetic of proportions? Can anyone think back to their geometry days? What kind of geometric trick? It's a standard geometric trick that you use all the time in mathematics. Exactly. From similar triangles, we get all these kind of proportions. So I go back to our whiteboard. Similar triangles is going to do it for us, right? Because remember, we can transfer lengths. So if we can generate lengths in one place, then we can just move it wherever we want. So straight away, that gives us addition, right? Because given a length, we can just start adding lengths. So we can do addition and we can subtract them away. So addition and subtraction comes for free once we can transfer length. How do we do multiplication and division? As Blake says, we have similar triangles. So if I let this be A and this be B and this be C and this be D, we have, what is it? We have A on C equals B on D. Okay, and so if, for example, we want to do B divided by D, right, then what would we do is we would construct a triangle of base D and height B, and then we would just we'd go along until we found our, let me get my eraser. We'd let C be 1, right? And then the height of that triangle is going to be B divided by D. And if you've got A over C equals B divided by D, then at the same time we have AD equal BC. And so, again, given, say, given A and D, if we let C be 1, then B is going to be multiplication of the two. So through similar triangles, you can do these addition and multiplication. Fantastic. Not only can you do that, but you can take square roots. Okay? And square roots are really important, right? Because that's kind of related to Pythagoras' theorem. It's related to quadratic equations. So, and from a geometric sense, quadratic implies area, right? So it means we can solve area problems. So taking square roots is really nice. So let me show you how. So the problem of taking a square root is solving the mean proportion. So given lengths A and B, you want to find x such that A on x equals x on B. And you should be able to see, well, that means AB equals x squared. So that means x has to be the square root of A times B. And so, for example, if you let one of those numbers be 1, then you're finding the square root of that number. And that's a pretty straightforward problem. So what you do, given A and B, you draw a line. So you add A plus B, right? What has area AB? What geometric object has area A times B? A rectangle. So this is the problem of the quadrature of the rectangle. Okay. So we put a semicircle on a diameter A plus B. We go to this point here, we put up a perpendicular, and that's our x. Okay, so this is very simple to do by a geometric construction, right? You just add A plus B, so you get a line, you get a length A plus B, you take the center of that line, you put your compass there, and you put it the other end at the end of the line, and you put a semicircle on the top of it, and then you raise a perpendicular above that point, and that gives you the point X. Okay. I think I might set that as a homework problem, but it's just to do with Pythagoras' theorem. It's pretty straightforward. Okay, so we can solve quadratics, but we can't solve cubics. But this is actually a famous theorem in mathematics, but it wasn't proven until I think it wasn't proven until the 19th century. So by cubic, that would be the problem of the double mean proportion. So that's then finding x and y such that you've got another thing in there. So one of them turns out, x I think turns out to be the cube root of a times b, and y turns out to be the cube root of ab squared. Or trisecting angles, that someone's going to be talking about it. Because trisecting angles actually turns out to be solving a cubic equation because we have this trig identity. So given sine 3 theta, finding sine theta involves solving this cubic. We'll see this equation later on, but that gives us problems. Okay, and so when someone talks about famous unsolved problems of Greek mathematics, it's all going to be, most of it's going to be involved with that. Or the other one is the quadrature of the circle, which is basically can't do because pi is not an algebraic number. Okay. So an important thing then when you've got doing geometry and arithmetic turns out to be the Euclidean algorithm, which we all know from number theory, and you don't really think of it as a geometric thing, but to the Greeks it was. So, so the whole idea of the Euclidean algorithm is to find the common measure. And we think of it in number theory terms, we think of it as finding, what is it, the highest common factor. The highest common factor, if you talk about geometry, is the common measure. Okay, so the idea is you have two lengths, and do they have a common measure? Well, you start taking the smaller length, you subtract it from the bigger length until you get the smallest thing there. If it goes all the way in, then the bigger thing is just a multiple of the smaller thing. But say you have a little bit left over, then you take that little thing and you go back to your original thing, and you start taking that away. And then if that goes all the way to 0, then you found the common measure. But if not, you find something smaller, you go back, and you just go back and forth. And if this process ends, you found a common measure. If you're dealing with numbers, that means you've found the highest common factor. Usually we just do it with integers, but you can do it for any number whatsoever. So for example, you could do it with 2 3/4, right? So 3/4 goes into 2 twice with a half left over. Okay, so you take the half and you compare the half and the 3/4. The half then goes into the 3/4 with a quarter left over. And now you've got a quarter. And a quarter goes into everything. And so a quarter is the common measure. Okay. Now, what happens if the process goes on forever? What does that tell us about the two numbers? It tells us that you're dealing with something irrational. Okay, so commensurable and incommensurables for the Greeks is kind of like the same concept for us as rational and irrational. So most of you have done 200, except Anna probably. So everyone knows that the square root of 2 is irrational, right? And in Math 200, you see the famous proof of why root 2 is irrational, right? It's a really super cool thing, and it's actually something I think every educated person should know, why square root of 2 is irrational, right? So can someone briefly outline the sketch of why square root of 2 is irrational? Anyone remember?
Don't you start by assuming it is rational?
You started assume that it is rational? Exactly. So we start off assuming, we assume that square root of 2 is a rational number, so therefore it's P over Q. So what do? Sorry? Oh yeah, assume that it's got no common factor, yep. Yeah, we square it, and so that means that 2 equals P divided by Q. What do we do next? Cross multiply, so we get 2Q equals P.
It would be 2Q squared equals P squared since P squared.
Thank you. I'm doing this as I sit in my pants. All right. So what does that tell us about the number P? It's even, right? So P squared is even, so that means P is actually equal to 2R. So that means 2Q squared equals 4R squared, which means that Q squared equals 2R squared. What does that mean? Q is even. So we've shown that P is both P and Q are even, but we assumed that they had no common factor. And so we've got a contradiction. So that means you can't write square root of 2 as P over Q. This is not how the Greeks would have done it. Okay. And in fact, square root 2, the first number that they probably found was irrational is the golden ratio. And the golden ratio turns up when you look at the pentagon. And let's see, I'm gonna embarrass myself by doing the pentagon. Okay, so this is a regular pentagon. Now, the regular pentagon has 3 times 36 degrees, 108 degrees for each angle. And so I write it as 3 times 36. So I'm going to put 3 dots for each angle. Each dot represents 36 degrees. Okay. And so what they proved was that the diagonal to the side of a pentagon is incommensurable. Okay, that means the ratio of the diagonal to a side is an irrational number in our words. That's like, we can think of square root of 2 as the ratio of the diagonal to the side of a square. So if you look at the ratio of a diagonal of a pentagon to its side, that actually gives you the golden ratio. Okay, so here's what we do. We are going to put in, this triangle here. This is an example of what's known as a golden triangle. You can do lots of interesting recreational math with this thing. Okay. So let's figure out what the angles are. So let me just briefly, because we cut up this, complete the task. Okay, we're going to put in diagonals. So how does this cut up the angles? Well, we've got 3 dots, it's 108 degrees, so there's 5 dots in a triangle. Right? 5 times 36 is 180 degrees. Here is 3 dots. So we need to put 2 dots into this triangle, but this is an isosceles triangle, right? So these angles have to be the same. So we can put 1 dot here and 1 dot here, and it's the same over here. 1 dot here and 1 dot here. And since this has to add up to 3 dots, there has to be 1 dot there. So the diagonals trisect that angle. I said they couldn't trisect angles except in a few set cases like this. Okay, and this has to be 2 dots here and 2 dots here. So it cuts up the angles quite nicely. And this is what I call a golden triangle, which is a 36, 72, 72 triangle. It's got lots of nice properties. But then what we're going to do now is we're going to take this angle down here and we're going to bisect it, because we know how to bisect angles, right? So we can bisect this and we form a little triangle here, which, since this is 1, this is 2, this has to be 2. And so this equals this. Okay, so now let me call things by name. Let me just get my notes so I'm not sure. So let's do the Euclidean algorithm then on the side and the diagonal of okay. So let's call this So we want to do so AD is a diagonal and CD is a side. So we want to do Euclidean algorithm on that. So AD is bigger than CD, so we're going to subtract CD away from AD. So when we do the Euclidean algorithm, we get AD minus CD, comparing it to CD. That's our pair. Now, CF is equal to CD. Oh, can anyone see another isosceles triangle? Because this angle is equal to that angle, so this, sorry for my bad drawing, this also has to be equal to the side. So we go AD minus CD is the same thing as AD minus AF, because all those sides are the same, but AD minus AF is FD. So now this is doing FD to CD by the Euclidean algorithm. And we're in an infinite loop now, right? Because we started off with a golden triangle. We did just one step of the Euclidean algorithm and we constructed another golden triangle. So FD to CD is the same, well, CD is actually now the largest. So maybe I should swap them around. So I should call that CD to FD. The next thing we do would be to take FD away from CD. But can you see it's just going to go on forever, because every time you take away one, you get a new golden triangle. And so you're just going to get an infinite spiral of little golden triangles, which is going to go forever. That means there's no common measure. That means they're incommensurable. That means that, in our terms, that ratio is irrational. You can do the same thing for square root of 2, but it just takes more work. The nice thing about the golden ratio is it's the easiest number to prove that it's irrational, because it's nice property. Has people seen the golden ratio before? We'll talk about it later. It's a pretty cool number. Okay, and I think am I pretty much done now? Yes. So last thing I wanted to show you was something that I'd left on Blackboard for you to look at. So this is all. So this is a little bit of math that someone might want to do for a capstone. This would make a good capstone problem. The idea of what polygons you can construct. So in Euclid, it shows, whoever does this in book 4, it constructs the equilateral triangle, the square, the pentagon, hexagon, octagon, the decagon, pentadecagon, whatever. Okay, and later on it shows how to construct the 5 Platonic solids. So it's a theorem, the Gauss-Wonzel theorem, that the first sort of, so this is early 1900s. It says that a regular n-gon is constructible with straight edge and compass if and only n. So you can have as many factors of 2 as you like. That's because it's easy to bisect things. But these are the only primes that you're allowed. You're only allowed with a single power, and they have to be Fermat primes. And Fermat primes are of the form 2 to the k plus 1. And it turns out that there's only 5 Fermat primes. If you ever find another Fermat prime, you'll become famous. Unlike Mersenne primes, which are like 2 to the k minus 1, where there seems to be infinitely many of those. And it's a famous thing in 1796. I think Gauss was maybe like 18 when he did this. He showed how to construct a regular 17 gon. And it was this is one of the things that convinced him that he should become a mathematician. He solved this problem. And at the other extreme, the 65,537 gon, someone actually wrote 200 pages of how you actually construct this straight edge and compass. And so if you click on here, it will actually show you how to construct a pentagon. You do diameter, you do perpendicular, you bisect that, you bisect this angle, you do it over here, and basically there's your side of your pentagon, which you then transfer around, and that makes your pentagon. Okay, that's all I had for today. Actually, longer than I thought.